today we're gonna start with the Design for Manufacturing workshop. Just let me start the presentation and we'll gonna show it now. Just a second. Just want to check if you can see my screen. And if you can see it, we're gonna start the presentation in this moment. Okay, perfect. So first of all, I'm going to introduce myself. My name is Katia Diaz. I'm an industrial and product designer and a design and engineering postgrad student at Politecnico di Milano. As well, I work for Cubic Fablab. I'm sure most of you have seen the Fablab before. And what we do is that we work with digital fabrication to turn ideas into realities and share knowledge. So we focus in explaining and guiding people on how to build their projects, as well as we give workshops and some other guidances. So if you have any questions about these, or if you want to stop by the lab, feel free to do it. You can see the information in the bottom of the presentation, or you can also follow us on Instagram or send us any WhatsApp or message. We're also happy to help any one of you. So we're one of the Fab Labs in Qatar, but we're part of the global network that complies more than 1,500 Fab Labs around the world with the same ideas of turning ideas into realities through open knowledge. So for today's workshop, we're gonna mainly be talking about 3D printing and CNC, which are the two most common fabrication processes. And I'm gonna be giving you some tips on how to design and how to set it up so you don't encounter many problems while printing your products or while machining your pieces. So first of all, we're gonna start with 3D printing. Okay, so I'm sure many of you are already familiar with what's 3D printing, but 3D printing is a fabrication method, and actually most of the time it's a prototyping tool, because the facilities to 3D print are still for low mass production. So we have to keep in mind that this is only a tool for prototyping or low scale pieces. Okay, so every 3D printer, it's built on the same way. Every 3D printed piece, sorry. So it all starts with a digital model or a 3D model piece that you can develop in a variety of softwares, or you can even download from internet. After you have this 3D model object, you have to follow the same process. You have to slice it, which means turning it into a G-code so the 3D printer can understand this G-code and then start manufacturing it. This is one of the additive manufacturing, and the term comes from how it works. So we have an extruder that deposits material, and it starts to add and create layers until you have your final piece. So it's adding material. That's why the name is additive manufacturing. Sorry, I forgot to say this before, but if anyone has any question, feel free to stop me at any time, or you can also use the question option in Zoom, and just feel free to ask me anything. I can repeat, or I can answer any question you have. Okay, so continuing with the 3D printers, we have many in the markets right now, but the most common ones are FDM, which means fused deposition modeling, and SLA. These two are the most common, and if I'm not mistaken, I'm sure most of you have already used FDM printers. So for this workshop in particular, I'm gonna be focusing in these two methods. If you have any question regarding the other methods or you want to see it, you can also stop by the lab, or I'm sure in Qatar there are some other places where they use SLS as well. And the process is a bit more complex, but if you have any question, I'm free to solve it for you. Okay, so all the as I said before, all the process begins the same with a 3D model, and then we get the blueprint, which is a G-code for the printer to understand it and start the process. So these are the two printers we're gonna be speaking about. First of all, FDM, as I mentioned before, it's fused deposition modeling, and this is the most common type of printer. You can see from the image how it works, but to make it more simple, I always give this example. So it's as if you had a hot glue gun, and you start making some circle, and then you make another circle on top, and then another on top. So you're depositing layers of, in this case, of glue until you make a structure. So it's the same with FDM printers. You have the filament, which goes through a hot extruder that melts the filament, and it deposits it in layers, following the shape you already sliced through a software. So whenever it deposits one layer, the print bed goes down to give space for the new layer to be printed, and then it continues on going down. So for FDM, what we use are filament. You can find a variety of filaments. You can use PLA, for instance. You can use ABS, nylon, wood. You can make your own filaments, some composites, TPU. With all of these new makers and new people getting into the 3D printing world, there's a lot of people that are starting to make their own filaments. We even had in the lab one girl that was making filament out of ceramic, and it's actually really interesting. You just have to take in consideration that some of these machines are not designed for this. So you have to be really careful while adding some filaments that are not the preset ones. So for SLA printing, this is a bit more complex than FDM, but as well the results are more accurate, even though the process is a bit longer. So SLA is stereolithography, which means that you have a tank of resin. For SLA, you only use liquid resin. So you have a tank filled with resin, as you can see in the bottom part, and then you have a UV light, which looks like a laser that goes through a layer. What this UV light does is that it cures the resin. So it's moving around, for example, curing a circle. Whenever this circle is cured, it's the opposite as FDM. So the printing bed lifts, and then it cures another circle, and then it lifts. So the actual print, it's stuck on top. Also, one of the downsides of these is that not most of the time, all the time, you have to use support. So by adding support, you also add more time for the post-processing and also more material. Resins as well are a bit more expensive than filament because of its high accuracy and also because of the mechanical characteristics the material has. So now I'm gonna play a short video on how Fdm works. So here we already have it sliced and the G-code. You put it into the SD and you can see how the extruder is starting to make layer by layer while the table here, it looks like it's lifting, but actually the table is moving downwards. And those are some examples. Okay, so this is one of the most common and affordable 3D printers in the market right now, the Ultimaker. Usually the filament in most of the cases, it's put it in the back. And for other printers are in the side. So the filament goes through here until it reaches the extruder, which is hot, it melts it. And then with the ambient temperature, the plastic or the filament automatically cools down and we have the final piece. I'm gonna just go through this slide because we're gonna need to take in consideration some of these features for the designing part, but this also depends on which printer you have. So the most important part in here for designing, in this case, is the nozzle diameter. So even if you have, for example, the Ultimaker 2, you can change the nozzles, but you have to be aware which nozzle are you using at the moment of designing. So in our case, at Cubic Fab Lab, we usually use the 4mm nozzle. So just keep this in mind so we can use this parameter for designing in the next slides. So whenever you have your 3D model ready to print, we go through this slicing process, as I mentioned before. And this is same as whenever you have, for example, a Word document or something you want to print in your house in paper. So what you do is that you have your file and then you click print, right? And whenever you click print, the setup windows pop up, and you select if you want it black and white, if you have a photo, paper, if you want it high quality. So Cura is that window to set up your, it's exactly the same. So what we do is just we pick up and drop our model into the table, and then we select the material, the nozzle size, and if you are aware of the setups, you can even customize it yourself, or the printer also gives you recommended setups. In my case, I will recommend you to, most of the time, use 30% infill in here, because we made some tests at the lab, and after 30%, it's super dense, which means that the extruder has to go more and more time in the same space. So this also increases the time of the printer, the material, and with 30%, we already get a really dense model. Of course, if you're trying to do something that is gonna be a prototype for a mechanical part, or something that is going to be in contact with another piece, maybe more friction or something, you needed to make it a bit more dense to prevent it from breaking easily. And as well, you have to take in consideration the material you're going to be using. PLA, it's a really good material that we use most of the time because it's recyclable, which is, it's really good at this moment, so we don't contribute to all the plastic and all the waste going on. But for some mechanical pieces, for example, if you want to make some gear or something, we will recommend you to use ABS. But of course, this depends on what you're designing and printing. Okay, so now we're gonna see the principles of SLA. This is one of the most common SLA printers. This is the Formlab. So in this area, you can see the container to place the resin, and underneath you find the UV light or the laser that hardens every part while the table it's moving upwards. This is the table. This process is way more accurate than FDM, but also requires more post-processing. So, and the timing, it's maybe double or triple the time. Since it's being printed face down, all the time it needs support, and your piece cannot be in contact with the table, with the printing table, with the bed, sorry. Some people say you can, but the resin is really sticky, so if you put it directly in the printing bed while removing, you have greater chances to break it. So you have to make a support from the table to your print, and then you have to make support in the entire print. This is, as I mentioned, printing face down, and it cannot print on the air, of course. So all of it needs to have support. What might take, for example, 2 hours in a FDM printer, it might take up to 5, 6 on an SLA printer. Of course, it also depends on the settings. In here, it's not density or infill, it's higher of the layers. So if you make thinner layer or smaller layers, the finishing is gonna be really good, but it's gonna take more time as well. So whenever you have your print ready, you have to put some gloves on, you have to remove it, and then you have to drop it in one of these containers to wash it or clean it. After it's been washed, you have to put it through a UV light, which is like a small oven, let's say, and rotates in a UV light to finally cure it. Because whenever you take it out of the print, it is still super sticky, and even if you press it a bit hard, your finger marks can print in the print. So we need to make sure it's fully cured before using it. This type of printing, it's really accurate, and there are so many type of interesting resins. What I find really interesting about these resins are that they can be used for a variety of items. For example, you can get resins that are designed to be used for molds, to get which the dentists use to get the mold of your smile, of your teeth. You can also get some castable ceramic that you can even put it in the oven to make some jewelry. So this printer has this variety of resins that you can use for a final product. But as well, the prices are a bit more expensive, the process is longer, but the accuracy, it's really good. So we're gonna watch a really quick video again on how it works. The video does not have volume, so no worries if you cannot hear it. So we see the resin in this area and how the light is going layer by layer. So the UV light cures one layer, then the print lifts. It cures another layer, then it lifts. Of course, here it's on a really high speed, because in the actual, in real life, it takes way longer. And you can see how all the small pieces need a lot of support. Let me show you that part again. You see in this area, it always needs a lot of support. So this is also material that it's been wasted in a way. Okay, so here are the features of the Formlab 2. Again, I'm just showing these because we need to know some things for the designing process. But if you have another printer at your house, just use the parameters or the features of your own printer, because of course it's going to vary. And here are some of the materials I was mentioned before, the castable resin, the tough, which is really good for mechanical pieces, high temperature resins, standard resin. We have flexible resin that you can use for sprint, for example. So these type of resins have some specific characteristics that you have to know before using them, but the final results are really good. Okay, so now we're gonna start with the actual design rules for your 3D print. Okay, so the idea behind having a 3D printer is, of course, printing a model. So how to get a printable model? You have two options. You either 3D model it yourself, or you go online and download it. Here I placed two online websites which are really good. One is Thingiverse. Anyone that has a model can upload it to Thingiverse, and it's free to download. If you want, you can tip the person who uploaded. If you don't, you just download it and use it for free, same as GrabCAD. And I'm sure there are a lot of more online websites where you can download your 3D models. And these websites have millions and millions of models. Whatever you imagine, I'm sure you can find it in there. But if you want to do something more personalizable or up to your needs, I'm gonna teach you right now how to 3D model for 3D print. So first of all, we're gonna quickly go through this chart. This is a really useful chart, so I will recommend you to go online and Google it and have it as a reference every time you're designing, because sometimes it's really hard to remember all of these small parameters. So in our case right now, we're gonna be designing for FDM, and for STL, which are the first two. So for FDM, this is a guide. Of course, you don't have to follow it as it is, but it's recommended. In our case, we found out that sometimes it breaks or it falls even before reaching this, but it's but it's a good overall guide. So here in FDM, for supported walls, the minimum thickness you can do it's 1 mm. You have to understand that it's gonna be doing 1 mm, and then the extruder is gonna be lifting and then printing again or depositing 1 mm. So sometimes if you do something really thin, by the time it reach, let's say 3 centimeters or 30 millimeters, it starts to bend because it doesn't have enough area to keep up straight. So this is the minimum, but as well, I wouldn't recommend you making something really high with this minimal thickness. The same goes for unsupported walls. The minimum thickness is 1 mm. And also you have to take in consideration that whenever the extruder is heating up the filament, it's melting it. So even though the nozzle is 4 mm, the material it's not 4 mm, because by the time it melts it expands to the side. So just take this in consideration for your designs. We're gonna see in a moment as well. Then for supports and overhang, the maximum you can print without a support is 45 degrees. This is what I mentioned before. Sometimes it even collapses at 40 degrees. But you can try it yourself. Depends on the parameter of your slicing software. Depends on the material as well. Then for embossing engraving, the minimum height can be 2 mm, and the minimum width, it's 0.6. Then for horizontal bridges, the maximum length of a bridge you can print without it sagging or collapsing, it's 10 mm, which is 1 centimeter. If you go past 1 centimeter, the bridge is gonna start to sag or collapse, and you're gonna see a lot of stringing, which is not going to work for your final prototype or your final product. Because even though you go through a post-processing, even if you go through post-processing, if you remove this material, you will remove the strength of your project, so it won't work. Then for the holes, the minimum is 2 millimeters diameter, and for connecting parts, this is actually really tricky. Again, it depends on your printer, but for example, if you have a box and then you have a lid that you want to put on top of the box, you have to make the lid 0.2 mm smaller, so it will fit perfectly. And even by making it 0.2 mm smaller, it will be really tight. So I will recommend you to play with your printer and see your own parameters. If you don't have a printer and you're going somewhere, then yes, use 0.2 mm less for parts that will go inside another or moving parts. If it's a part that does not to be attached and it will be moving, I will even increase it a bit more. Then for escapes and holes, you have to leave a small space to remove the support, because otherwise you're gonna end up with a solid cube, for example. Minimum features as well, it's 2 mm, and the tolerances may vary from 0.2 mm approx. Then for pins, and we're gonna also talk about this in a moment, about the pins, because the minimum you can make a pin is 3 mm, but 3 mm it's still really tiny. So if it's gonna be for a mechanical part, the first time you use it, it's just gonna break. So I'm gonna teach you what to do to prevent this in the next slides. Okay, so we're gonna start with some tips for designing. First of all, vertical holes. So you have to take in consideration that that whenever the printer is making the layers of material, the layers of the filament expand since it's melting. So here, this circle is the filament, but whenever it's being deposited, it widens. So if we want to make a circle, for example, this is the original circle, we have to make it a little bit bigger to prevent it to shrinking due to the compression of the layers, compression and widen of the layers. Most of the time, the slicer takes this in consideration, so you do not have it to make it yourself, but it's good to understand that the wall might increase by a few microns, and if you want to make a really accurate hole, it's going to be really complex to achieve it because you don't know how much it will melt to the sides. So if you want to make a really precise hole, what we will recommend you is to make the diameter a bit smaller and then drill the hole to the correct diameter, because it's, as I mentioned, really hard to achieve the diameter you want at once. So for bridging, as I show you in the chart, the maximum we can do is 1 centimeter or 10 mm. If you pass this range, this is what will happen. The material will start to sag and your part will lose its strength. So there are some solutions to avoid the sagging of the material. One of them is adding support under the bridge and then remove it by post-processing. Temporary support, of course. And the other one, if your model allows it, it's flip it. So if we flip this, we won't need any support at all. For example, if we flip it 180, because it will be building on top of its own material. I do understand this is not the case for all the models, but when possible, try doing this. Okay, so in the first slides, I talk about the nozzle of the printer. In the case of the Ultimaker, the nozzle we use at the lab, or the most commonly used nozzle, it's 4.4. So whenever you're printing, it's same as what happened with the holes. The material is adding material on top, so it's pushing the one below and it's expanding to the sides, as you can see in here. So the bottom layers are compressed and expanded, and we don't get a straight wall. So to adjust this, what we need to do whenever we know what is going to be the base of the 3D model, what will be touching the print bed, we need to make a chamfer of 45 degrees in here, of half the size of the nozzle. So in our case, our nozzle is 4.4, sorry. We have to make a chamfer of 0.2 mm at 45 degrees. So if we make a chamfer in here, then it will expand and it will reach a straight line, a straight wall. So this is one way to correct this. This is called actually elephant leg. So this is, or elephant foot. So this is one way on how to correct the elephant foot. Sorry, just to mention again, For example, in SLA, since it's printed downwards, we don't have this issue. So if what you're trying to make has to be really accurate, that's also another recommendation to use SLA printing instead. Okay, so for overhangs, one of the solution we will recommend you as well is try to flip it so it does not need any support. But if the model does not allow it, just keep in mind that the maximum you can print without support is 45 degrees. After 45 degrees, you can see in here, the material will start to sag again. So another solution for this is adding support that can be removed by post-processing your pieces and or flipping the piece. Okay, so the vertical pins. Whenever we are designing a piece that has a pin, just take or try your best not to make any pin smaller than 5 millimeter diameter, because whenever the printer is making the layers, it's never fully full by the material. It has some cross sections just to build another layer on top. So we already have a really tiny diameter, and beside that, it's not a full of filament or plastic piece, so it will break really easy. So if it's something that is gonna be constantly used, one of the recommendations is to add a fillet in here, so it's more secure and attached to the body. Or you can evaluate if this is an option for you, but just drill a hole and add a off-the-shelf pin if it's gonna be in constant use. If it's just a prototype, you might solve it by adding a chamfer, but if it's gonna be in constant use, we will recommend you to just add a shelf pin afterwards in the post-processing process. Okay, so these are some advanced tips, which actually are not that advanced, but it's good to take in consideration. So here in the example, it's really simple and logical on how to do it, but whenever we have more complex pieces, you have to evaluate what you are gonna risk and what you will have to put in some accesses to have a better result. So in this case, for the hole orientation, it's better to put the hole in a vertical axis, as you can see in this picture, because if you put it sideward to the side, we will need to add support, because the layers cannot be built on top of an empty space. And then removing the support from these small holes might be really complex. You're gonna waste a lot of time trying to remove every piece without tweezers. So if you have the chance just to flip it so the holes are in the vertical axis and you are not in the need of any kind of support. If your component has multiple holes, just try to focus in orientating the smallest hole in the vertical axis, because might be the one harder to post-process afterwards. Okay, now we're gonna be talking about splitting up your model. So for example, if you want to print a sphere, since this is more than 45 degrees, and we already saw that the maximum we can print is 45 degrees, and as well, due to the shape, it cannot be in contact with the table, otherwise it will be flat. We need to add support. So in these cases, it's recommended to split your model in two parts. By doing this, you will save tons of time and material as well. You won't need any support. You won't have any overhangs, and the printing time will even be faster. So just split your model in two, and then in the post-processing, you can just glue them together, and you will have your complete model. Now for the direction. So we have to understand that FDM printing, it's when and plastic are have an anisotropy characteristics. This means that the mechanical properties depends on the direction of the filament, and each surface behaves different with load. It's the same if you have a log of wood. It's more resistant if you put it upwards or vertically than if you put it horizontally, because wood also have anisotropy characteristics. So here are some examples on how to orient it if you're gonna be adding load or if you're gonna be printing for mechanical pieces. So you have to think in advance. What will your object might be doing, or which forces are gonna be added to your pieces and are gonna be applied to your pieces, and then you can rotate it on what is more convenient. So if we're gonna be, it's gonna be bending load, this is the way to place your print, because if we put it in this direction, it's gonna be more weak, or it's gonna break apart easily. So just take in consideration which load is gonna be applied, and then try orientating it based on this. Okay, so this is just a recap of the rules we just saw in the past slides. So if a bridge exceeds 5 millimeters, sagging or marks will start to appear. We can split the design for avoiding this, and we can just join it in post-processing. Then for critical vertical hole diameters, it is better to make a smaller hole and then just drill it to the accuracy or to the final size you are expecting or you want. And the addition of support will also allow FDM printers to print wall angles greater than 45 degrees. Remember that 45 degrees is the maximum you can print, but if you can not go higher than 40 degrees, that will be safer. Also, again, it depends on your settings and on your slicer software and material. Include a 45 degrees chamfer or radius in the bottom part of your print, the part that is touching the build plate, to avoid having the elephant foot, which is this small bump in the bottom part. With application with vertical pins, if it's got something that is gonna be in constant use, or something that is gonna be for a mechanical prototype, try inserting an off-the-shelf pin instead of printing it, because printing it is just gonna be too fragile. And splitting the model, reorienting the holes, specifying the direction of the force that is going to be applied, or the direction in the build plate, can lower the cost, speed the printing process, and improve the strength, print quality, and also avoid some post-processing. By post-processing, I think you understand, but it's the process you do after you remove your piece from the printer. It might be sanding it, it might be removing the support, it might be painting it, it might be gluing it together. And whenever we have all of this ready, we go through the slicing software, which is the one I showed in the previous slides. We select our printer, our material, our infill, and we save it to the SD card, where we place inside our printer and just click print. Here you can see I didn't add any support, because even though the shape is a bit complex, the angles are not higher than 45 degrees. So that's one of the advantages of 3D printing, that you can fabricate pieces that with other technologies will be really expensive or really complex to make the molds, for example. So for small productions, this is really effective, and for prototyping as well. Okay, so now we're gonna go to the second part. I'm gonna be explaining you a bit about CNC machine, and also some parameters we need to follow to get better results, and also to save some time, money, material, and headaches as well. Okay, so first of all, what is CNC? This is a term really commonly used, but CNC stands for Computer Numerical Control Machine, which is an electromechanical device that manipulates tools, usually beads, around varying axes. Most of the CNCs you will find in maker shops or fab labs are 3-axis CNC machines. Of course, if you go to a more specific industry, you can find 6-axis. But for now, we're gonna be focusing on 3-axis CNC machines, which is X, Y, and Z, mean the depth of the machine, of the bit. And this is one of the 2 ways that engineers and makers can produce physical parts from a computer design file, from AutoCAD, from using Rhino, from using SolidWorks. And the other one is 3D printing, which we already talked about. So the main difference between a CNC machine and a printer is that the CNC machine, it's a subtractive process. What do I mean by subtractive process? So, but this, I mean that you have the material, let's say a plank of wood, from which the bead will remove material by rotating on a high speed, and this is the main difference between additive manufacture and subtractive manufacturing. In additive, as we saw in the 3D printing, we add material. Here we have the material and subtract it to find or to get the shape that we designed previously in a design software or in a computer software. So this also depends on your machine, but usually you can achieve high accuracy and tight tolerances. On the other hand, CNC machine can produce high volume of pieces, and it's the most cost-effective way of producing metal prototypes, even compared to 3D printed. So this gives us the chance to produce more on a short time and on a cost-effective way. Okay, so here are some, here are some of the most common things or parameters you need to know before designing or for designing for CNC machining. First is the depth of the cavity. I'm gonna go a bit faster now because I'm running a bit short of time. So usually you use a bit, and the bit has a diameter. So the deepest you can go is 3 times the diameter. Let's say your bit is 1 mm, the deeper you can cut with that bit is 4 mm, because otherwise it's gonna start to vibrate, it's gonna have chip, it's gonna hit the walls. So to make it safe, I recommend you not to go deeper than 3 times its diameter. If you need to do a deeper cavity, there are some specific tools you can use for this, but we're not gonna talk about that in this specific workshop. Then for the walls, there's a minimum wall thickness, which vary depending on the material. For metal, we recommend a minimum of 8 mm, and for plastic, a minimum of 1.5. Also, you have to take in consideration that some plastic might need to have higher parameters, because plastics melt faster, and the bit is rotating and creating friction. So friction might melt the plastic, and this will not give us the results we are expecting. For small features like holes, we recommend 2.5 millimeters. Of course, if you want to make something more accurate, you have to take in consideration some specific tools, or you have to speak with the person in charge to use another machine maybe, because CNC is also used to, for example, make PCB boards, which are smaller, of course, than 2.5 millimeters. But for this, you also take in consideration other factors and other tools. So for general CNC manufacturing for wood, plastic, we're gonna stick with 2.5. For more specific items like PCB, just speak to your manufacturer, or you can come to the lab and we will support you in that regard. For the tolerances, you have to stay with the standards. Why? Because I'm gonna continue to the next slide so you know what I'm trying to say. Okay, it's not here. Sorry for that. Just try to keep up with the standards, because the beads already come in standard size. So this is gonna be more cost effective for you and faster. Otherwise, we will need to change the tools. It will be a most complex process, and set up the origin again. It might not fit in the place you were expecting. So just try to stick with the standard parts. Then if you want to do text and lettering, we recommend you doing engraving instead of embossing. Emboss is what you see in here. Engraving is having the letter under the material, inside the material. So this is faster because you don't have to remove all the area around the letters, and also try to use simple sans serif, the fonts that does not have these tails or curls, with at least 20 points. So it's easier, and as well, many CNC machines have already pre-programmed routines for these fonts. so it won't be a problem. Of course, if what you need is embossing like this, it can be done, but just take in consideration that the size of the bead won't permit to make close angles. So here you will have a small radius, same as the diameter of the bead. And this is what I was talking about. So in the CNC, we cannot make straight corners. So you have to make a radius that is more than a third of the diameter. So if your bead is 1 mm, the radius needs to be 1.3. So it gives space for the bead to cut smoothly in. In the outer parts, corners can be done because the bead will just go in one direction and another. But for internal holes, you have to know that all of the time we're gonna have this radius. If you want to do something that it's gonna fit inside and you need that sharp corner, what we like the lines you see in here, what we will recommend you is to make the angle or the radius inside. So the sharp corner will fit perfectly instead of just reducing the angle and preventing the other part to fit in. Also, we spoke about this before, try to make the walls a bit thicker. The thicker the better. The minimum for metals is 0.8 and the minimum for plastic is 1.5 mm. And try to limit the length of the thread. So as I mentioned before, the diameter of a bead might be 1. So the highest it can, or the deepest it can cut is 3 times its diameter. So you can see in here, this is 1 and this is 3. So we have to respect this because otherwise it won't leave space for the material to come out. It might vibrate, it might break. So just respect this all the time. And for holes and standard pieces, just remember to use standard sizes and try not to specify tolerances only when necessary, because this will increment your costs a lot more, because the person that is machining your piece has to set up all of these and follow a more complex process. So in case it's not really necessary, please do not add specific tolerances. Try to keep the number of machine setups to a minimum. That means try to make everything in one axis when possible, so we don't have to lose the origin while rotating. And try also to avoid small features with high aspect ratio. Same as the letters we were talking, instead of making embossing, try to engrave it. This is faster for the machine, and also this prevents your pieces from breaking. Because remember, the bead is gonna go around all these parts. So with the vibration, if your piece is not properly secure, it will just break it. So try to avoid this unless it's really necessary. And what I was talking about lettering, it's better to engrave it instead of embossing the text. If you need to emboss it, it's fine. Just remember that the inner corners are not gonna be possible. And that's it for today. Thank you so much for joining our workshop on how to design for manufacturing. If you have any question, you can also contact us, or you can stop by the lab, by Cubic Fab Lab, which is located in the industrial area, or just feel free to contact us in any of these ways. Me and my colleagues will be really happy to assist you in anything you need, sorry. And thank you so much. I hope you enjoyed it as much as I did. See you another time.